My name is Robert Grant, and I am the CEO and chair of Crown Sterling. And we have several members of our team here as well. So we're going to actually start off a little bit unorthodox, but we're going to start off with something kind of very exciting. And that is, we're going to do a demonstration of cracking public key encryptions. Basically, there is a simple mathematical equation that underlies all of the world's public key cryptography, which represents virtually any transference of data that happens on the planet today. Data or money. So this literally protects all of our assets. And because gold no longer backs our money since Bretton Woods in 1973, what really is backing our money today is, you could say, public key encryption, because there's no other means to transfer money today. This is the math, and it's funny because we actually surveyed CISOs, right? Chief Security Officers of corporations. We surveyed about 500 of them total through research done with the Ponemon Institute, and we asked them, both on a conference call that was real time and then also separately, if they could articulate the mathematics behind encryption that does all the protecting that we have for money and assets and everything today. And what percent do you believe actually said that they knew the mathematical equation behind public key encryption? 30%? We've got the head of Verizon Security over here, Chris Novak, who's on our advisory board. So what, you said 1%? Yeah, it's shockingly small. It was 5%. 5%. Now these are the chief security officers of some of the largest corporations in the world. And you would think that they would know the math. But the reason why they don't know the math is because the math has literally been taken for granted. It hasn't changed since, does anyone know the year? 1978. So Bretton Woods is when Nixon got rid of the gold standard on money. And in 1978, public key encryption was started, right? So Diffie-Hellman key exchange occurred so that we could transfer things. And the public key is like a mailbox. And only the recipient has the key to open that mailbox. So the sender can send and encrypt their data to that mailbox. And what happens is they'll often encrypt it with another encryption inside of it, which is called AES, Advanced Encryption Standard, which is for stored data. It's not for transferring data. So you need a public key wrapper. If you know how to crack the public key, you can just grab the private key of the stored data, and you crack the stored data as well. So the public key is the linchpin, and it depends on one simple math equation that is prime 1 times prime 2 equals composite number, same as A times B equals C. This is what's called a discrete logarithm, and it means that it's a one-way street function. So if I have these two prime numbers, then I can solve and crack this key very quickly, right? So if I'm a holder of the private keys, this would be the private keys. If I'm holding the private keys, then I can open the public key, okay? However, if all I see is the public key, and by the way, this is actually published by companies. It's published by banks also. You can go on bank websites sometimes and actually see what the public keys are. They're numbers that the bank believes are so large that they can't be cracked in any reasonable amount of time. Like it would take 1,000 years, just like this Australian fellow said on this video. So basically, if you know these two numbers, you can solve it quickly. That's why it's efficient. If you don't know these two numbers, it takes a really long time to do a trial and error test, to test every number smaller than this number, right? And that's what this discrete logarithm is. It's trial and error. Okay, so that's how encryptions are cracked. But we're going to give you a demonstration now of cracking encryptions, and we're going to get some keys issued to us that we've never seen before from the RSA library, right? And we're going to have Joseph manage this process for us. So come on up, Joseph.
Yep, absolutely. First of all, it's a great crowd, RG, right?
Yeah.
Holy cow. Thanks for coming, folks. Looking forward to talking to you shortly. So we've got two of our programmers here. Jesse, raise your hand. And then we've got Eric, raise your hand. So Jesse, you're going to live on this screen, And by the way, folks, I apologize. Just given the nature of the room, some of you that's on that end may not be able to see all of this screen and vice versa for this screen, so I apologize for that. So Jesse, you'll be on this screen. Eric, you'll be on this screen. And by the way, so Jesse basically went to an RSA-oriented site, and he basically was able to download code that is used to actually generate the public key. You can also generate the private keys from that as well. Any of you that are so thrilled by what you're going to see today, you have an interest in running public keys and private keys, we can show you how to do it. All right? But so not necessarily a secret, but I want to just let you know this is very much a public effort. So Jesse will go ahead and run a public number using the RSA code now. And then what will happen here is that he then will patch over that public number to Eric, who then will put that public number in our one of our particular algorithms used for decrypting that public number. And then you'll actually see that process working by way of percentage to actually get, to finish up. And the results of that will be that he'll actually have 2 private numbers. And then we'll try to match up the private numbers that are rendered from our algorithm to make sure they match up to the private numbers that Jesse pulls from the algorithm, okay, from the source code. Okay, Jesse, why don't you start? So you're going to be on this screen here. You're going to go ahead and run the public. Let me know when you've got your public number. Okay. I wonder, where's the pointer? Yeah, sorry. Okay, and your public number is right here. Okay. Why don't you go ahead and pass that over to Eric? And then Eric will get the number, and Eric will be on this screen here. And Eric will put it in his algorithm. Let me know when you've got the number, Eric. Yep. It's kind of like that Jeopardy, right?
He's gonna airdrop it.
Yep, he'll airdrop it.
There it is.
Very good, right here. So Eric has got the number. Is that, I can't see, is that, you have the number there, Eric? Okay, so now you're going to go ahead and put that in our algorithm. Have you done that?
Yep.
Okay, very good. So we should start to see a percent. I can't see,
Yep,
is that up running? Okay, very good. Yep. Okay. Yep. So it's running. We've done this a few times, so we sort of have an idea how long it takes, but I won't tell you that. Let's just say how long it takes. Okay. Where are we right now? What percent are we there?
It's already done. It's now just deduping.
Okay, very good.
So while we're waiting, can you explain the relevance of the disk space available?
I'm sorry,
The
what was
disk space.
Yeah. As long as we're waiting, can you talk about the disk space, why they keep showing us disk space?
Well, it's running on local devices, so I don't know. I just think that's a part of the screen that we've just elected to show. Yeah, it's really not relevant, I don't think. Okay, it's done?
Okay, it's done.
How long did it take?
52 seconds.
Okay. Now, when you go and you access the code to produce the public key, it'll also give you the private key. The actual true nature of the private key is a combination of alpha and numeric characters. So Jesse, show us the private key. This is a private key. So Jesse now will run that through a translator, which then will render the numeric values, much like you see here. Okay? And then we'll see to make sure that Jesse's numeric values match up with Eric's values. And there we go. So we got prime 1 and then prime 2. Eric, can you go ahead and read out what you have for prime 1? Maybe just the first portion of the first number and then the last portion of the last number. Or the last portion of it.
Go ahead and speak into it.
Test?
Yep.
So for the first 5 digits of 1 prime, it starts in 30862, and that number ends in 14961.
Okay. Okay. Okay, very good.
Second one.
Okay,
And
okay.
for the other prime,
Yep.
it starts in 27047,
Yep,
and it ends in 07857.
great. Do we got a match? Yes, did it match up?
Yes.
All right. Should we do another one, or are you guys convinced?
You've seen it already.
Yeah.
We did 2
Okay.
in the last session.
Yeah. Anyway,
We can do one more. Do one more.
okay, let's do it again.
Go ahead, Jesse. Generate one more. Now, we'll say this, that this is 256-bit encryption that we generally crack in less than a minute. We're publishing a paper on this. It's going to go through peer review. And also, we crack 512-bit in as little as 5 hours. And we have some new techniques that we believe will allow us to crack 1024 and 2048 very, very rapidly. And we're going to talk about some of those in the course of this math presentation that I'm going to give. And we just spent the last couple of hours talking about with those that were already here.
So Jesse, you're running your code? Oh,
I actually already have the information.
Okay, very good. I'm behind. Okay, very good. Eric, so you have the number, and you put in an algorithm?
Correct.
Okay.
We demoed this for the Department of Defense last week. It's funny, they were planning on seeing 5 because they gave us 5 of their numbers. And then after we showed them 2, we said, do you want to see more? And they were like, no, we're okay, we got it.
And isn't it that anybody in this room could hand you a 256-bit RSA key and we would do the exact same thing?
Yep, exactly. You could do it with a 512-bit also.
512
We
as
give
well,
you
yep.
the answer in a few hours. Yes.
If I'm right, then, if someone had the decryption ability and someone sent a message and intercepted the message, which is the nature of the internet, then in a short period of time, under a minute, they could actually decrypt that message, whether that's a password or whether that's a financial balance, and gain access to something that's supposed to take hundreds of thousands of years under normal circumstances to be able to do. Is that right?
That's right.
And that's a great comment, Mark. This is one of the reasons why we don't randomly do these things. We make sure when we do it, they're very controlled settings and know what we're doing. We do not accept strangers' keys for the purpose of then giving them the private numbers. We don't do that.
Could be somebody, we're okay with the computer generating it from the internet or something.
Did we get it?
Because that's just like a random key. Cool. Someone that says, hey, we want you to crack this number, it could be someone's bank account.
Okay. How long did it take us, Eric, on this?
49 seconds. 49.96.
Okay. What was the first one, by the way? I forgot to ask.
50, 52.
Okay, very good. Okay. And then let's go ahead and compare them real quick.
And these are on just laptop computers. This is standard computing.
Okay. Why don't you go ahead and read out just the first portion of P1 and then the last portion of that, Eric.
Okay, so for the first portion, it starts in 28011 and ends in 86783.
Okay. And
For
then-
the second number, it starts with 30579
Yep.
and ends in 04779.
Okay. Is that matching up, Jesse, with yours? Yeah. Okay. What do you know? We matched up again.
Basically, this is the first time that we're actually releasing this publicly. So we've written a paper and we're submitting it for peer review. And I'm going to take you through the contents of that paper and how we came to this solution mathematically. And that's basic discovery.